Chemistry in the AM. Yeah.
Aggressive today.
Aggressive today. Buckle up, feel the G's as we take a journey through intermolecular forces between molecules. And the three types that we're going to talk about is hydrogen bonds, which is actually a type of polar bond. More about that later in London forces. Okay. We have already had a little introduction to this the other day. And polar or non-polar, we have to look within a covalent bond and see geometrically, do the electronegativity differences cancel out? Polar bonds, do they cancel out? And so this is why we needed to know our structures. We kind of played around with that, but hey, I'm leaving you with this as a warm-up. Are these molecules polar? So you're going to look up. And do you remember that for the purposes of comparing along a row and stuff like this, the H is in between boron and carbon. So like right away with OH in water. Which is more electronegative, the oxygen or the hydrogen? Which is closer to fluorine? Oxygen, right? So you're going to draw the plus sign with an arrow towards oxygen. And geometrically, I have these drawn in 3D fashion. So you go through that. I'll give you guys a few minutes here, and we'll take them up. Okay? All right. Oxygen and hydrogen in water. Polar. But let's see why, because I'll also want an explanation why. Now you can always guess, but you won't get full marks. You get one. So this, more electronegative oxygen. And you see what happens there? Basically, the two add up for a net dipole. So then it's polar. There's a net dipole. If the two pushes or pulls don't cancel each other out, it's polar. Now, in this particular case, it's definitely polar because if it was CH4 or CCl4, it would cancel out, but that's not the case here. So in this case, remember I said hydrogen's kind of between boron and carbon. So it's not a huge difference. I'm going to just put a little arrow here, but there is one. Okay, those two push this way. Then the chlorine is definitely more electronegative. I'm going to put a larger hole. Now, I don't care about the size of these. But you see all together, and I'll hold up a model with this geometry. If you had, and I'm holding it this way, this model, right? And I'm pushing here, like those highlights. And then I'm pulling this way, pulling this way. Everything will kind of come this way. Does that make sense? Don't use your imagination a bit with these vectors. So I'm going to put the net dipole kind of like that. It's 3D, so it doesn't come out correct. It's definitely polar. Nothing cancels out. Nitrogen bonded to nitrogen is 100% covalent. You can't even put any polarity difference or electronegativity difference one way down. So it's non-polar for sure. So anything like Cl2, F2, O2, etc. You can't keep non-polar when it's you can't tug of war with yourself. Nobody wins. Okay. So this is where we get or what we're going to with the geometry that we studied earlier. We've got to apply it this way. And then, what do you guys know about polar molecules and biology? Because I know a lot of you have taken biology and talked about this. I'm just wondering what we know. Talk to me. Hydrophilic. And hydro, water. Philic, love. Water loving. Yes. Anything that is polar will dissolve well in water. Non-polar, not so much. So, oil on water, what do you know about then oils? Yeah, it floats. So what do you mean of what do you know about polarity in water? Are oils, there you go, fats and oils and stuff are not polar, so they don't mix with water, which is water's polar. So it'll, like dissolves like, and we'll come across that. Okay, so you guys know a little bit from biology. You may not remember everything. And we take a slightly different look. So when we flip this around, this is something else that came up in biology, hydrogen bonding. And it's not inside the molecule bonding. This is inter, between molecules, or between parts of molecules sometimes. With a really large molecule like, yes, DNA? Absolutely not, but we'll talk about that. Hydrogen is the positive. So let's read this. This is perfect timing. All will be revealed. If hydrogen is bonded to nitrogen, oxygen, or fluorine atoms. Yes? Now, I'm not saying giving charge. And remember, these are partial. The hydrogen, that bond, that I drew the blue arrow, because I'm talking on here. So this bond here represents two electrons covalently bonded. The hydrogen contributes an electron, the oxygen contributes. The electrons involved in the bond are drawn more towards the oxygen than they are. It doesn't steal it, otherwise it'd be ionic. It's not possessed 100% exclusively by the oxygen. So that means there's a slight positive end at the hydrogen. And we're going to actually see that it's a little more than most polar molecules, or polar bonds. And we're going to have something, hydrogen bonding. Water's the best example. So good thing you clarified this. Back to this, if hydrogen's bonded to nitrogen, oxygen, or fluorine atoms, a really strong dipole force can occur between these molecules. This very strong type of dipole force is called hydrogen bond. So, first off, this only happens when you have HN, HO, or HF bonds. Anything else is just polar bonds, but it's strong enough in those three scenarios that we give it a special name, hydrogen bond. This intermolecular force is stronger than other dipole forces because the hydrogen's lone electron, you know how hydrogen just has one electron? It's the first thing on the periodic table, one proton, one electron. And it's attracted to the more electronegative ion. This leaves the one proton, one electron, while the electron is sucked in towards the oxygen, for example, with the water. And it leaves the butt end of the hydrogen out, and that's just a positive proton. So it's got a really strong positive end to it. So the example, as I mentioned, water molecules, they have hydrogen bonding between them. Water is a liquid at room temperature due to the hydrogen bonds between molecules. For example, the methane, similar mass, but it's a gas at room temperature. It's not polar, so it doesn't have something that holds the molecules together as tightly. So that gives water some of its peculiar properties too. So I've got hydrogen bonding there. Now I used ammonia molecules, but you can see how you can probably adapt that diagram to water, right? O's and H's. So what it is this end, and this is why I don't like the musical note, the nitrogen end is the slightly negative part, and the hydrogens are the slightly positives. Here, so I said for the whole molecule, the hydrogen end is positive. Well, the next nitrogen molecule, and I'm showing the intermolecular bond, it's just a dash, just to show you there's some attraction. They're not connected, no, truly connected, they're just attracted to the next ammonia molecule. Same kind of diagram with water, and I'm not going to draw everything in. It'll be okay, the hydrogens are positive. And then the next oxygen, well, you can see it will be there, but not. So I'm showing the hydrogen bond with that black dash. Like dissolves like, I already used the phrase. And you guys brought it up, that's why. Polar molecules dissolve well in polar solids. Non-polar dissolve best in non. Oil and water. Water is polar, while oils are not. So you can't add oil to water and expect them to mix much. You have that salad dressing, like Italian kind of dressings and stuff like this, which vinegar is basically mixed with water a lot. So it's basically water and oil. You shake it up, and it stays mixed for about 2 or 3 minutes, and then it separates, doesn't it? You guys know what I'm talking about? Okay. And it'll just naturally do that. You give it a minute or two, and it separates, right? Have you ever had really oily, like if you're ever working on a car or something like this, you get really black, oily stuff on your hands? How do you take it off? Have you ever used something other than water to get rid of that? Fast orange or something? Yeah, that's a good one. Soap has peculiar properties because it has a little bit of each. Has a hydrophobic part and hydrophilic part. Water, so polar and a non-polar. So soap is really good for removing grease, yet it sort of floats on the water though when you get greasy water from doing dishes. Okay. Also, you can't just get, if you get really oily hands, and I'm always thinking when I do something mechanical, stuff like this. Um, yeah, just water the garden hose and stuff. It just, you just wipe it and it just smears all around. I end up wiping it on my pants. But I'm smart. I don't. Sometimes I do this. If I have really black hands, I've taken just something quick like WD-40 as an oil. Do you know what I'm talking about? I've actually sprayed my hands and got rid of the black stuff all over them. Brake cleaners for washing hands, you mean? Yeah. And I've used gasoline before too, stuff like this. Whatever's handy. Gasoline's non-polar. I mean, I don't light a smoke or anything like this. It's more just handy because I'm right there and I want to get rid of the stuff. I'm not recommending you wash your clothes in gasoline. Don't do that. But I mean, yeah. So like dissolves like. We use that. And so here's something. What do you know about Crayola kids markers that you used to probably use? Maybe your parents still don't allow you to use the regular markers. Um, you know the washable markers? They're different than the other markers, right? So they wipe off quickly with water, really easily, right? What does that tell you about the ink in a Crayola washable marker? Polar or not? Because they wash off with water without even soap. Polar. Most markers, like if I have a Sharpie, I do. Sharpies don't come off that easy, do they? What are you telling me? Non-polar. Have you ever had to remove Sharpie marker from your skin or something like that, or from something? How do you do it? How do you remove it from a table? Hand sanitizer, maybe. There's alcohol and stuff like this. You could, I've used hairspray. That's what one of my children was about three or four or five maybe, at my brother's place, and he didn't have children at the time, so it wasn't set up like this. He had a bunch of Sharpie markers and a really nice silver one. One of my children drew on their face, made himself, I wanted to look like a cloud. Anyways, so we used hairspray to get it off, and it was still even tough. But, you know, that's the way. It's about the only time I've used chemistry outside of the classroom. That's not your concern. I'm not going to. My children want you to know things I would. Forces between non-polar molecules. London forces. It was my son, but one of my three sons. Yeah. London forces are the weak forces between non-polar molecules. They're caused by a momentary dipole. So there's no polarity. Like when you have water, you've got a positive and a negative end. I'm using the simplest example, helium. Okay? You imagine for a brief moment, these electrons are just shifted to the right, just by random chance. They give a weak electrical attraction, about 1/10 the size of a dipole force, okay? So that's what I've got here. So this would be a slightly negative end because the electrons in that region more for the next second than it is here. So this would be slightly positive and vice versa. But it's very fleeting and it changes within seconds, okay? Non-polar molecules tend to be gases at room temperature since London forces holding them together are weak. But all molecules have some type of London force. It's just that if it's a polar molecule, the London force is massive, totally. Okay. So here we are. Any questions about this? London forces is what you use for non-polar. It just explains. Okay. In summary, inter and intra. Intra, inside. Ionic bonds, covalent bonds. Inter, between molecules. Hydrogen bonds, which if you say something has hydrogen bonds, you're not going to also say polar because it is a type of polar. So there's hydrogen, polar forces, then love. Okay? Everything you can list 11. Okay. I'm going to stop this.